the bottom of your Zoom screen. You can also upvote existing questions. I'll raise your questions with our presenter at the end of the webinar. Today, we are thrilled to be joined by Dr. Natalie Robinson. Natalie is the co-PI for Project 4, Sea Ice and Carbon Cycle Feedbacks, and a marine physicist at NIWA. Thank you so much for joining us today, Dr. Robinson. I'll let you take it from here.
Great, thank you very much. Just let me share the right screen. Okay. So it's my pleasure to be speaking to you all today. Thank you for tuning in. I was given a pretty open remit about what I was going to talk about today, so I decided to sort of celebrate the discovery and innovation aspect that characterises Antarctic research, and just share a few stories and meander my way through to getting to my research. So we're fortunate now that we can sort of enjoy this view of Antarctica and understand what that means. So Antarctica is basically made up of two types of ice. We have the glacial ice that sits on top of the continent itself, called the ice sheet, and then surrounding the continent we have a second type of ice called sea ice that forms from the ocean itself. And there's enough sea ice that in the height of winter it basically doubles the size of Antarctica itself and then shrinks away, almost all of it shrinks away again into the summer. But I'd like you to cast your imaginations back to a time before we had this sort of information, and in fact before people had started contacting the continent in person. So I'm going to start with James Clark Ross, who captained the Erebus. And so here's a quote from Roald Amundsen. He was already writing 100 years ago, but looking back to a time 50 years before that. With two ponderous craft, regular tubs according to our ideas, these men sailed right into the heart of the pack, which all previous explorers had regarded as certain death. So if we come to their description of the sea ice when they first encountered it, so which they identified as the pack, Erebus and Terror, these were the two ships, were in an ocean of rolling fragments of ice, hard as floating rocks of granite, which were dashed against them by the waves with such violence that their masts quivered. So those are quite evocative words. But what really brings this home, you imagine the audience back home listening to those words. And then they see images like this. So I think there was real value in including people whose specialisation was in visual documentation at that time, and they were able to bring back images like this that really brought home what it was that these men and these ships were up against. So if we look to their first experience of that other type of ice, which the front of the ice shelf, which is where that glacial ice extends out over the ocean, they called it the barrier. Ross saw a low white line extending from its eastern extreme point as far as the eye could discern to the eastward. It presented an extraordinary appearance, gradually increasing in height as we got nearer to it, and proving at length to be a perpendicular cliff of ice between 150 feet and 200 feet above the level of the sea, perfectly flat and level at the top, and without any fissures or promontories on its even seaward face. So again, you've got some quite interesting words there, but if we look at an actual image of what that looks like, you can really see what the front of the Ross ice shelf would have looked like. And there's some people down there in the bottom right-hand corner, just to give you some scale. We have this towering cliffs of white. And I do like their little pithy postscript on that. we might, with equal chance of success, try to sail through the cliffs of Dover as to penetrate such a mass. But why I brought James Clark Ross into this was because I believe this is the first documented, recorded interaction with supercooled water, which is the subject of my own study. It was so cold that while the crewmen were chipping ice from the bows of Terror, a small fish was found frozen in place where it had been thrown against the ship's side. So we're not talking about water that's sort of quite cold and a few drips of it have landed on the side of the ship and then gotten cooled down further by the atmosphere. This is water that's already below its own freezing point, and it just is waiting for a nucleation site and it's able to snap freeze. So they won't have identified it at the time as supercooled water, but looking back in hindsight, we can see that this was in fact supercooled water. And again, we have quite a pithy little postscript again. Terra's surgeon and naturalist, Dr. Robinson, tried to retrieve it for analysis, but the ship's cat was a little quicker. So putting myself in the picture, you'll only be able to observe supercooled water in this way where you have an ocean circulating underneath an ice shelf and where it's able to melt there. So I quite like this image of me because it's got Scott base for reference, so that's circled in the red there, and we're looking almost directly south. If I just draw your attention to this line here, so to the south of that, we have the ice shelf, and in front of it, we have the sea ice. So right where Scott base is this intersection between these two types of ice that make up Antarctica. And we have the ocean freely circulating underneath the two and sort of connecting them. If I just take away that red line, hopefully you can still see the distinction between these two regimes. And this is the setup that you need in order to observe supercooled water. So just looking at it from a satellite perspective, so here's Scott base again on Ross Island. So Scott base sort of sits at this intersection, this quite interesting intersection of land, sea ice, which is open ocean in the summer and covered in ice in the winter, and the ice shelf. And what we've been able to identify in recent times is that there's quite a strong exchange flow between the sea ice regime and the ice shelf regime that the ocean provides, which goes right past Scott base and through McMurdo Sound. So we have this significant oceanographic feature that was in need of a name. As I said, there's this exchange flow between these two regimes. This strait, as it's now been identified, is approximately 25 kilometres wide. It reaches down to over 900 metres in places. And so we've got a throughput that's sort of comparable to Cook Strait. And of course, that Cook Strait's been named for a long time now. So why wasn't this particular strait, which is of similar magnitude, ever named? Well, probably just because it was covered by ice and you couldn't physically see it. So my colleague, Craig Stevens here at NIWA, decided that it needed a name and started looking. So in the tradition of naming Antarctic features, he went back to see what sort of events may have happened in this place that the strait could be named after. And so his first proposal to the naming board was Pony Camp Strait, in recognition of the camp that Scott set up to house his ponies. And I won't go into it today, but it's quite a story of drama and events and excitement, really. Anyway, that was not accepted as a name. But if we just quickly have a look at, on the left there we have the oceanographer who was there with Scott at that time, Edward Nelson, and he's collecting data, and you can see that those more recent photos of me collecting the same sort of data 100 years later, well, some things just don't change, do they? But anyway, continuing the search to naming this strait, we decided to put up Tim Haskell as a namesake. And Tim has a very long association with Antarctica, and his service to Antarctic research has been awarded with the New Zealand Antarctic Medal. He's worked at the DSIR and Callaghan Innovation, and really I could fill this talk with just talking about Tim's work, but haven't got time for that. But of relevance to my talk here is what we're calling Camp Haskell. So this is a series of converted shipping containers that Tim devised. They get housed at Scott Base, and then they get pulled in this train out behind a bulldozer out to your site on the sea ice, where they get set up as a camp, as you can see in that photo below. So this has really revolutionised the way that we can do science in Antarctica. And so yes, the naming board accepted this proposal, and here you can see Tim wearing his Antarctic tartan tie in a promotional image, but we've got this nice story of when he found out about the naming. It was all set to be gazetted, and he was actually at Scott Base at the time. So Craig gave him a call on the phone, and so he was able to look out over Haskell Strait from the Scott Base bar and discover that it had been named for him. So that was quite lovely. And then a more recent round of innovation, in addition to those converted shipping containers, we now have some that are set up as laboratories inside, but with the addition of a lift out floor. So we can lift out the piece of the floor and melt our way down through the sea ice underneath, as Greg is doing on the left here. And then you can see that we're left with a continuous and easy access directly into the ocean without needing to go out into the weather. This does lead to some interesting encounters. On the left there, a Weddell seal has found our hole, and it's very convenient for him to be breathing. I can tell you I got the fright of my life the first time this happened, having a 200 kilogram animal coming up through a hole in your floor and then breathing his little lungs out was quite a surprise, especially as I had no idea that it could happen at all. But moving on to the data, so working inside that shipping container gives us an opportunity to collect quite a lot more intense data than otherwise possible. So what you're looking at here, if you look down through the page, you're looking down through the water column from 0 to about 300 meters. And then across the page, that's time progressing. And so what we have is we've sent our instrument down and up through the water column 300 times in a 24-hour period, and you're looking at all of those data with each point coloured by the temperature at that point. And so over 24 hours, we've got quite a nice little tidal signal there. And so collecting this length of data lets us see how things evolve in time. You compare that to just that little hole in the sea ice that I showed you previously, and you might only be able to collect half an hour's data at the time. So if you were collecting it, say, in this period on the left, you can see that you might end up with one particular idea of what the water column looks like. It's fairly homogeneous all the way from 0 to 300. Whereas if you were to come along at 12 hours later, and collect the same sort of data, you can see you might end up with quite a different idea of what the water column looks like. And the same is true for the salinity. If we pick those same two periods, again on the left, the salinity of the water pretty homogeneous, whereas it's got much more structure and character 12 hours later. But what's quite interesting is that when you use those data, the temperature and the salinity, and you convert that to a measure of how supercooled the water is, you can see that it's no longer a problem. These two profiles are pretty much showing us the same thing. And so those blue shades at the top are the water that is supercooled, coming down to the white where it's right at the freezing point, and then below that everything is warmer than the freezing point. If I take away and show you all of the data, you can see that what was quite a variable signal in temperature and salinity has now resolved itself to being quite a stable signal in supercooling. And this really demonstrates the effect that the pressure is having. So what I've been doing recently is taking all of the temperature and salinity data that have been collected across McMurdo Sound and translating that into a measure of the supercooling. And you can see, hopefully you can see my pointer. This is where the water is flowing out through, out of the ice shelf cavity and into the sea ice regime. And so we've got this concentration of supercooled water close to the ice shelf cavity. At this point, I'd just like to quickly introduce Dr. Pat Langhome, also awarded the New Zealand Antarctic Medal for her services to Antarctic research. And I was fortunate to have her as my PhD supervisor. And Pat came to New Zealand originally because at that time, the British Antarctic Survey were not taking women to Antarctica, whereas the New Zealand program were. So it's really great that we were able to have her, and she's been excellent for New Zealand science. She also joins a tradition of celebrating New Zealand women scientists in New Zealand. And I'd just like to quickly note that in 2017, the 3 new science labs at Scott Base were named in honour of 3 pioneering women in Antarctic science. And I do hope that this naming survives the Scott Base redevelopment, and that these women continue to be honoured at the new Scott Base. So if we just look at one of the papers that Pat was the lead author on, what I want to draw your attention to are these green circles and triangles, because these were the data that Edward Nelson was collecting 100 years ago. And Pat has put them together with much more modern data. And so you can see that although their instruments may have been fairly rudimentary by our standards of today, they actually fit quite nicely, a remarkable set of measurements. And I'd also like to draw your attention just to these 2 experiments in 2003 and 2009, which Pat spearheaded, in which it was these were wintertime experiments, so possible to do the work all the way through the winter and study the sea ice as it was actually growing. But the main gist of that paper is understanding the distribution of platelet ice. Now, this is a special type of ice that will only form in supercooled water, and supercooled water that's flowing out from underneath an ice shelf. And so on the right there, you have Pat's map of these special platelet ice crystals that have been incorporated into the sea ice cover. So it's a measure of how much of the sea ice cover is made up of platelet ice. And you can see that we've got this concentration sort of emanating away from the ice shelf cavity in a similar manner to the supercooled water itself. So just a little bit about the platelet ice crystals themselves. On the left here, you have my first attempt to take photos of platelet ice crystals just to try and show everybody this strange phenomenon that I was studying. Whereas on the right, these are photos from 2016, where I was able to take with me Gabby O'Connor, who's a professional artist and documenter. And so you can see that the wonderful images that she's been able to collect for me. Actually, she took about 3,000 images of individual platelet crystals. And they're not just pretty images. If you look at that one in the middle, you'll see that they're actually scaled images. So I can use image processing software to turn these into data that tell me about the size distribution of these different crystals that they're carried with the water, and as they grow bigger and bigger, eventually they'll become buoyant enough that they want to float up and land against the base of the sea ice above them. And they come up in their billions and billions. So the more we can understand about them, the better we can understand this system. And of course, just a little three-dimensional portrait that Gabby's taken, which shows the internal structure that these platelets create. Another image of hers shows what the ocean will see as it flows past the base of this layer. In this case, the layer had accumulated up to about 3 meters thick. If we step back down into the ocean, so I've got a bit of a wider view looking up. So now you're seeing sunlight that's filtered through the snow and then the sea ice and then this layer of platelet ice underneath. And often it can be turned green like this, and this is because it's been colonized by algae. Actually, that's the same seal that I showed you before. If I take you right in and you have a look, this is at the intersection between the bottom of the sea ice and the platelet ices that have accumulated underneath it. And you can just see it's absolutely chock-a-block full of algae and gunk because this structure, this platelet ice, leaves open spaces but provides a protective environment that the algae can colonize. And then the detritus from the algae makes its way down and eventually into the ocean, where it provides a food source for other parts of the food chain. And it's actually this relationship between the physical structure and the biology that depends on it that is going to be my main focus over the next few years as part of the Antarctic platform. In terms of other future work, I just wanted to quickly introduce Christina Hulbe, who has been studying over the past several years how the ice coming off Antarctica first connects with the ocean and what effects that has. So this is actually a figure from this Stevens et al. Paper, which was focused on this other opportunity for ocean access all the way through hundreds of meters of ice shelf at this HWD2. And then the present focus, and for the next few years, is at this new site, another site on the Ross Ice Shelf grounding line. And I'm hoping that I'll be able to make a small contribution to that understanding. Christina has also enabled some international colleagues to come in and be part of that. They're also interested in the biology aspect, but with a much broader focus. So they have designed this underwater robot that's able to go down a very narrow hole all the way through those hundreds of meters of ice and into the ocean that's hiding underneath. But their ultimate aim is for other icy worlds. So this is a moon of Jupiter, this is Europa, which has a global ocean, and then outside of that, a global ice shell, which is many kilometers thick. So you can see why Antarctica's ice shelves form the best analogue that Earth has for an icy moon like this. And the reason you might be interested in going there and finding out more about it is because of that global ocean, all that water, it has potential to harbour life of some form. So that's what their search is about. And then just finally, another sort of future aspect. I do quite a lot of schools outreach, trying to bring Antarctica to kids. And that one on the right, it's a whole set of noodle boxes that I left hanging in my kids' rooms the first time I went back to Antarctica after I'd had them, and there was a box to open each day that I was away. It was just kind of for me remembering that there's a future that relates to all of us, not just Antarctic researchers, and the role that Antarctica has in determining that future. And the last one is just an advertisement for a play that's currently touring New Zealand schools. I'm done now, but I'd just like to finish giving you a little video, and that'll give you a chance to pop your questions into the Q&A if you like. So what you're going to see are lots of different images of the platelet ice that I've collected myself, and all the sounds that you hear, you'll be able to hear a tick, 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 which is my instrument doing its thing. But everything else are the Weddell seals. So if you haven't heard them, listen in, this is quite neat. And I reckon at this point, the seal was imitating or trying to communicate with my instrument. And that's all I have. So thank you very much for listening in, and thank you for having me.
Thank you so much for that presentation. That was amazing. I think no matter how many times you hear that sound of the Weddell seals under the ice, it never really, the novelty never really wears off. And thank you for bridging the history and now. I think that intersection between the early oceanographers' work and what you're doing now is fascinating. So we do have a couple of questions. I'll start with one about a satellite image that was shown earlier. So where you showed us the different types of ice in the land from above, what were those dark patches that we could see on the image there?
Oh yes, okay, that's quite cool. Those are called polynyas. They're sort of windows of the ocean where the sea ice gets continually blown away and off the surface of the ocean by the katabatic winds. So that means that the ocean is continually exposed to the cold atmosphere. So you keep forming brand new sea ice in those windows. And then it's that water that gets, so you end up with lots of brine being rejected, and that's the water that ends up going into the ice shelf cavity and starting off the melting that we end up seeing as supercooled water coming out again. Kind of this two-way connection.
Brilliant. And oh, we've got lots of comments here. A few people saying you're awesome. Thank you so much for that awesome presentation. Yeah, someone else has said thank you for the James Clark Ross connection. And we just want to talk about the noodle boxes, I guess. And Natalie, obviously, your family is so important to you, and they're wonderfully supportive. How do you juggle spending so much time in the field and connecting with your family back home?
Well, I have to give a shout out to my mum, who enables me to keep working in Antarctica. She comes down and stays with my family. Of course, my husband's supportive too. There is not a lot of direct connection, and not in the sort of communication we enjoy back home. But it is possible to have satellite phone conversations. It's a bit more expensive than your regular cell phone. But I don't find that my kids actually engage that well with it, with just a phone conversation. They're a bit young at the moment, so yeah. It's 5 or 6 weeks away from them, and then we're very glad to see each other when they get home again.
Yeah, and I'm sure they're filled with questions from what you've got up to in the field. Yes,
and then they like to go back and tell their mates at school the latest that I've got to tell them.
Yeah, well, we've got someone here who's asked a question who said, how are platelet crystals different from the ice in a drink?
Well, actually not essentially different at all, because it's you only retain the fresh part of the water. So although it's coming out of ocean water, the crystals themselves reject all that brine as they form. And because you've got this nice thin sort of leafy structure, there's lots of space for that brine to completely get rejected, so you really don't end up with pockets of salt left in it like you do with the regular sea ice cover. So actually, you can eat it, or you can put it in your drink if you want.
Perhaps not recommended though. Now, more on the ice crystals. Can you tell us a little bit more about how the ice crystals were redesigned by Gabby O'Connor, and where we might be able to see those ourselves, or sort of what's happened with that project?
Gabby has done a lot of work bringing those platelet crystals back to New Zealand in a sort of sense. Obviously they'd melt if she brought the real thing. There was one amazing exhibition that she had at Pātaka here in, Pararua, where she created, with the help of many workshops full of school children, they created plastic platelet ice from, those clear folders, document folders that have got no colour, but it's just a plastic sheet. So she used those to make, and packing tape, clear packing tape, make hundreds and hundreds and hundreds of these individual platelet crystals, and then created a inverted carpet of these crystals. And it was amazing actually how well they reflected the light in such a similar manner to the real platelets themselves. And so classes of kids could come in and lie on the floor and look up at this inverted crystal structure above them and learn what it would have been like in that same environment that I've been showing you today. I don't know off the top of my head where you might be able to experience that now, but if you email me or something, I can get you more information.
Brilliant. And we've got another question here. What do you see as the most critical piece of research that's needed to help us understand current and projected changes in sea ice thickness and extent?
Yeah, Well, understanding the thickness is key. We know that over the past 40 years, the first 40 years of the satellite record, we know that the sea ice took up a little bit more space. There was a trend towards slightly greater extent, which seems like a puzzling thing when you know that the ocean that it's forming from is warming. Why would you have more ice in a warming ocean? But actually it's not even necessarily more ice at all, because we haven't been able to until very recently been able to estimate the thickness of the sea ice from satellites. So you can see that it's how much of the ocean it's covering, but you can't actually see how thick it is. So it's possible that it was actually the same amount of sea ice, but just stretched slightly thinner. Work that Pat has been heavily involved in with her international colleagues is really understanding how we can put better estimates on the thickness and match that up with the satellite observations. So in terms of sea ice, thickness is the big key, and when you put snow on top of the sea ice, that makes the measurements that much harder. So that's where I think it's great to be putting effort in right at the moment.
Brilliant. Oh, that's unfortunately all we've got time for today. Thank you so much for sharing your time and your wisdom with us, Natalie. It's been a real privilege to listen to your presentation and absorb some of your knowledge. I'd also like to thank all of our attendees who joined the webinar today. Next week, we'll have Richard Levy, lead PI of Project One, join us. Same time, same place. We'll update the platform website this afternoon, and this webinar has been recorded, so if you missed it, or if you know someone who might enjoy it, we'll post the link on the platform website this afternoon. Take care. Ka kite.